All right. And the answer to that is. Okay. All right. Now it's okay. The answer to that, see if it's still there. Yes. Okay. So the ODE that you get, right? In fact, in the traditional work of Bender and David, when they developed global solutions, they actually got estimates here where the best shot was to say that BK would go to M sub K, but the negative term by Jensen's inequality goes to 1 plus the positive number. That positive number is exactly what you get here. Gamma is the strength. So it's gamma over 2, and that is K minus 1 is the order of the moment. Now, if you look at this number, right, when gamma is equal to 0, which is maximum molecules, that would give you a linear term, which in this case we include. But in the case of with the estimates of Devillet and or Bender, in that case you would have the same order as the two of them, but you have a formula, and that was the wise. So the success is because gamma is positive. And above 2, we don't know how to conform moments in the same way. So it's interesting. By the way, Hinani identified like the rate 2 in a paper that what he called the tertiary conjecture is almost true, because in that case, he could an entropy effect normally, but has no physical meaning except that for polyatomic. So so we extend it to the range as far as we do it with that. But that's the explanation. So the negative term. So and then you go to the classical books of ODE. Any ODE with a super linear negative term. All right. So the bottom line was that clarifies why it's hard potential. That clarifies why it's global, and it also this estimate provides a very precise description on what are these, on how these numbers, so here is essentially we identify the equilibrium is the 0 associated to this polynomial, we define the equilibrium solution, and then it's very easy to write things in terms of the equilibrium solution because you have it in this form. So for propagation, you have the maximum between the initial data K and the equilibrium. And for, so is how we split it. But you also have generation, and that is rather spectacular. And it's also because we have super, I mean, maximum molecule propagate, but cannot generate, and which is gamma equals to 0. Ooh, here it's 1 over that parenthesis. But what happens is you can start with 2 plus moments. I mean, you start with the number of moments that you need. Exactly 2 plus, we can make it work. And so you have to have a little bit more of the energy, just a little bit more on the tail. And then what you can obtain is that instantaneously in time, you get the moment generation. So the moment generation formula has something that, of course, degenerates as time goes to 0, because at time goes to 0, you would only have 2 moments. However, as soon as time becomes positive, you get any. And that actually is a property like that somehow, the heat equation enjoys and that if you can if there's, fundamental solution and that you can involve and it's even analytic solution. So in any case, so the equilibrium can be fully characterized, and that actually characterization comes up later in the way we do the rate of tails, and I'm going to talk about that in a minute, and how that things extend to the other 2 parts. So the sequence of doing the Bressan approach now is fully complete. Bressan could not actually target carefully the subtangent condition. It's a technical aspect, and you have to find a particular set that is not empty for perturbation of a solution that has 2 plus. In this case, the answer is you have to find what is the set. The set is, we can do it to 2 plus 2 gamma and a little bit. And then for that, we can actually use the Bressan theorem, just using the estimate of the moments of the collision operator. Just take the moments of the collision operator and check that it satisfies this Helder condition, subtangent condition, and the one-sided Lipschitz condition. Then it gives you uniqueness within this set. And this set is well prepared because it has the convexity, and it has the fact that you, by pinning down the L1 norm and the L12 norm, you are saying what are these conserved quantities for any element in that set, and then you get conservation for free. All right. And then what we do, we extend by density. Once we have this existence, we do a density argument into lowering the Lebesgue weight but being approximated by functions that are in this set. I should put this, yeah, okay. It's in this set, yeah. And so the omega, so it's functions that are coming from that, and then you do density approximation, and you look at the topology. So while they're dense, you look at the estimate in the topology that corresponds to the lower shell, and then you use the fact that for the sets, for the solutions that are in the set omega, you have generation and propagation, and that is needed to be able to lower and get an estimate. So that actually closes the theorem of Bressan, and that was not well clarified. Okay. So all right. So that what else? What else we can say? We can say, and I have this about 10, 12 pages of the proof. I will not. I don't think even in the graduate course you can expend time for that without boring the audience. But you work and you work and you work, and you can actually manage to show the following: that the sum of moments, right, is actually summable. Partial sums of moments are finite, and that basically means that the distribution is going to have an exponential weight, a positive exponential weight, which means if you think that weight should be divided by that term, is that in L1, your probability distribution decays Gaussian line. Not Gaussian line, decays whatever it comes up here. And so for propagation, you can get to the Gaussian. For generations, you cannot. You can decay like e to the minus v. For propagation, you can get all the way to the Gaussian distribution. But what is interesting is what is the rate? And the rate we fully classify, and you see it here. And here it depends on, this is the coercive constant. And here it's a rational function of the coercive constant that it would degenerate to 0 as x equals to 0. But we pin it down. And I'm going to show it later on in another slide, because I didn't want to cram so many slides, but we probably need to have it. And so essentially, I mean, this is also in the review paper. But again, all of these details may be, not important, but if you think for a minute, what we can do, and we're finished writing all of this with Ricardo Alonso, is that that you can actually get and reconstruct the decay rate to equilibrium and calculate the spectral gap, and the spectral gap is associated to the tape. Okay, and that was well understood. The question is, what is that rate and how do you get it? And we can actually what I'm going to show you next, because I keep on saying I can do it in the mixtures and so on. I have to show you that I can do the moments, right? And I have to do this contracting, this angular average. So it's the energy identity, the moment method, and the exponential, and see if I can sum up. The summability of moments I would like to stress, it really depends on whether you have global estimates here or not. So you're stuck in the sense that I can do it for hard potentials. Question, what will happen for soft potentials? If I have soft potentials, then the whole thing blows up, because what happened, and that's why you look at the work of Catholic 40 years ago, which he did with graphs of 45. And he said there is no spectral gap. So we do know you cannot push it. And part of the reason why you can understand is at least that if you look at this estimate, you would have here a negative contribution for which the gain wins, and there's no way you can actually control of how this variability of moments would actually. Okay, so that it's a you may think of it a little bit in those terms. So this is the estimates for generation. They are slightly different, but you can see you start with an initial data that has a little bit of more than 2 moments. It's the moment of the initial data, we call it, and then you can actually generate any tail of order S, but S cannot pass actually we should be someplace 1/2 in any case. But in any case, what we get here is that this is up to order actually up to order down. Oh, here it is. S is up to down. So you can not even for gamma equals to 1, which is classification in the Gaussian, in the other case, in the propagation. Here you can unfold. So, all right. The LP theory. Let me just say a couple of things for the scalar case, and then I will show a little bit better before. It says, well, can you actually get an equation of this kind, like we did for now Y is the LP norm, maybe the LP norm with the weight. Can you get it superlinear? And the answer is no. Actually, that was recognized by Lyons, and it's the work of Lyons in 1997, what is called the gain of integrability. And somehow what you can do is the gain of integrability means this in that sense. I guess is, I mean, one student says, why gain of integrability? Well, it's the integrability of that you get, right? That's what you need to get done. And it's that the positive term, you can actually work hard. That's what we learn all from Lyons and pick up, and to get this a little bit lower than, so to do interpolations, to do splitting of this part of the collision operator, which is have the positive contribution of the binary part, and then show that this equation actually is integrable. Okay, and with Ricardo, we are able to prove again this and put a constant here by doing interpolations, and these are some new things that we use the ability to split the kernel of the mass of the angular kernel in putting most of the mass near the singularity and the rest very neutral. So it's like concentrating. So concentrating the estimate by assuming how I'm split. And okay, so the gain of integrability estimates are going to be always, so in a sense, if you want to do this successful things, is that the negative contribution has to be in the measure we are doing this on. And that enable us to do, again, with an ODE here that would have global bounds, but now you're going to be putting LP estimates, but then we can actually, we learn even to do the estimates with a weight that would corresponds to an exponential weight, and then we also get the LP exponential weight. And that is what you really need to do, the L2 estimate and pass it to Sobolev to calculate the magnitude. So it's all related to that. So there is one new ingredient here, and this is not, we have not found it, well, or not written in the way we write it here, which is, but I should say that in the work of Lyons, he said there exists a constant. And we did something with Alonso in 2011 where we actually found that. So we know exactly how much it is. But this is another estimate, which I didn't use it for the lower, for the propagation of moments, but this estimate has to do with finding a lower bound. And if I can parse it to you, it's not very complex, but we realized we could not find it. And we could not find it, and some people have been somehow using it and but never saw it written. And this lower bound, essentially what it does is the following. You pick up, you can also take it for gamma equals to 0. And so you get, so this has nothing to do with the Boltzmann equation. This has to do with the choice of the Banach space. It's more like the Poincare constant, right? The Poincare constant doesn't care about if it's going to be in a PDE or not, right? It just is an estimate on the Banach space. And so what you do is you take functions whose mass and energy cannot pass these two numbers. You may assume, okay, take the mass. I mean, I'm not even talking about conservation at this point. A posteriori will use it, and that's what exactly I need to say, right? Because I do it for functions that are in the solution space. They would have that this is a constant and this is another constant. And clearly here, you see, this is not the Banach. No, it's not the Lebesgue weight. This is just the absolute value. So at this point, we said we want that the F and the classical energy, if you wish, of F are bounded between these two numbers that are fixed, that the mean is 0. So it's renormalized. This works for spacing homogeneous cases. And you assume a little bit more of a second moment. Again, like, you want, I mean, essentially what we do is we don't use entropy to do the conservation, but if we do have entropy, we know by that condition that the initial entropy is bounded, and so it's being propagated because the solution is propagated. So in a sense, it's an analog condition that we found it easy to do, or I don't know, surprising, because we don't want to deal with entropies for all those fancy places for inelastic collision. So in a sense, it's a good thing. And but the result here says the following: if I have these three conditions, then I look at the convolution of my function with, and here would be v, because the convolution is v minus v star as I'm going to be using it. So I'm convolving with this polynomial function. Gamma is between 0 and 2, and that has a bound from below, which is the bracket to the gamma. And that is crucial to put the lower bounds that are going to form a superlinear ODE for my estimates whenever I use them. And I could use them for moments. We chose not to do it because traditionally it was not. But in the paper of polyatomics and mixtures, we actually start by using this lower bound. And the reason is that you cannot start just with 2. There are much more things that take into account. So and in addition, the proof is constructive, and we know exactly what the bound is. And that is, again, it's very good because that aids to the recursiveness. So if you want to do even, for computations, right, you really know exactly, if you want to get a reliable computation and you have a reliable constant, use it because you're going to get much more accurate decay rate to live. So in any case, so the Kahneman representation is the other ingredient. This is in the classical case. And what I bring it to your attention, because the Kahneman representation aids us to start by the L2 estimate in the single species K. This is the work we did in 2011 with Ricardo. And essentially what we have is that we use the Kahneman representation and we apply it to the Q plus operator where gamma is the Kahneman, is here. When you look at these quantities, these are, these variables, if you parse them, it's really written center of mass and relative velocity. So Z is going to be the clearly the angle, and Z plus X is the the cosine of an angle. And so they basically allow you to do this calculation. So I'm going to, I mean, you can find out in the literature, and then we actually can trace exactly where these constants come from if you actually find what are these integrals. We do the mixtures, we have to find these integrals, and you will see that I'm showing one case that here would appear constant that depends on the mass ratio. And it turns out that the mass ratio happens to be 1/2, and 1/2 of the species coincide with all the estimates we have. So it really, saves save us the day, or give us confidence that at least the estimates are more. Okay. And so then the gain of integrability comes from, and this is really what it came from the inspired by the work of Leon, but we use a little bit different techniques that allow us to start to get estimates. And let me just focus a little bit on what we want to do. Is here is what we call the Dirichlet integral. You want to estimate the LRK, with K is the Lebesgue weight norm, and so that for that we were able to write exactly this form of this estimate, get a control. This is what we know how to do now. This is recent work on 2022. Estimate this term by splitting the kernels exactly as I said here in a decomposition, which after being symmetrized, you want it to be, is the good part, as we said, to be 0 in the ball of radius epsilon, and to have so you're going to put the mass in the outside of the ball of radius epsilon, and here you want it to be in the L1, including the ball, to have very little mass, no, very little mass, of the order epsilon to the gamma. That gamma is the gamma. It has, it's like you have to tie up a little bit for this. And so then you go the restoring interpolation, and we get a way to get a control by a term that depends on the collision kernel, basically on the angular part of the collision kernel, but also on the potential and on the splitting and how much you're going to put on each part. But you can actually do it for any bit that is in L1. So if you try to do it in L1 wrong, you cannot. You have to distribute the mass of it. Okay. And then you get this estimate, right? And this estimate put us back to an ODE equation that basically can calculate. So at the end of the day, the technique is a little bit repetitive, but you go back to our graduate life, postdoctoral life, and so on. And all we did when we do energy estimates that we call is to find ODEs for the Banach norm. Okay, and that's one more. But we are, so then we do the propagation of L infinite. We can make it work as well. For that, it's not an energy estimate. For that, and I don't have the details of the proof, we really use the Lebesgue bracket and the representation of the collision operator in a strong form, which is what you think the strong form of the collision operator always is related to Kahneman integral. And indeed, we use the Kahneman integral to start with the L2, but then you start to gain the other powers by interpolation. So ultimately, it allows us to do in a strong form, looking at these coordinates that I show you before, right? Which is how much was deviated V prime minus V, and V prime star minus or minus V star. You have to choose to get the right form, but you get it one. And then you get a control by the initial data. Okay, these L infinite estimates were proposed by Arcueil, but if you go to the way Arcueil wrote it 50 years ago, in the early 70s, he actually uses kind of kernels and so on. It's a very elaborated construction, and it's pages and pages. Now this is reduced, and it breathes on the fact that we can, so I don't say, but these estimates here depend not only on the estimates that you get here on the data, but also on the L1 K estimates that you construct. So it's that you start to split, and you gain the integrability by doing, Young's inequality, propagating, and interpolation, and so on. And then I'm ready for the binary mixture. And in the binary mixture, I'm going to show you how, with the interaction law, I can construct a normal system. And if I have that, and what is the Banach norm? It has to be a vector value norm, right? And then can I incorporate all of these things? And the answer is yes, because once I have the moments estimates, I know the sum. Well, all it matters is that it's a binary. Okay. So in the case of the Boltzmann equation, we have an arbitrary number of species, capital I, and so we have I capitals I times I system of equations. And each binary operator are going to take this form written in the strong form. We assume that the collision kernels actually are symmetrics, are functions of the gamma ij and bij. That is the only symmetry that we assume. But the outcome is not. I mean, it's not true that because you are going to have this ansatz, right? That the estimates that you get from BI from QIJ are the same J. The reason is here you have, so when you put this prime in this setting, it could be a bit confusive as you read it, and in the paper we try to clarify that carefully. But when you look at V, think of VI. And when you look at V star, think of VJ. And they have different mass ratios. So the symmetry is broken because, okay? So here you see the, so the diagram, what is the difference? What you saw in the elastic case is that if this would be elastic, the blue ball comes up to here. So this small gray comes up to here, and this one comes up to here. And then you get that the red lines are this, and this, that, and it's a rectangle. Yes?
The energy, the internal energy, is that deterministic?
No, here is the mixture without a stability parameter. That's polyatomic, and that is another one. Okay? So the problem here is that now, right, before, when I look at the relative positions, the pre-post with respect to one reference. So while I write here prime and V, here I say VI prime minus VI, and here I see VIJ minus VI. And I have to trace down all these coordinates very carefully. And what you get to see here are very different conformations of what is that relation. In the scalar case, this is 1/2, and here you have 1/2 and 1/2. And then you have that one is, both of them have a minus sign because I chose it to write it this way. I could just write it in the other way. But if not, it would be just 1/2 U minus U sigma and 1/2 U plus U sigma. But that's absolute value of U sigma. And then what happens on top and on the bottom is the same. And we thought for a while that this could not be done for, we got staggered. And Mrs. Howard, we're going to extend that. We didn't know. Well, we have to revisit it and really dissect the diagrams to pick up the things and see if the estimates that you do for every pair carry on. And the answer is yes. Once you have it, and you get it. Okay? This is work with Erika de la Canal, who graduated, she's a student of mine who graduated 3 months ago, no, 6 months ago. And he's working in a company for machine learning, writing software for you remember? That's right. He likes it. Oh yeah, he really does. Right. But she's an extraordinary mathematician and is doing great what she's doing. Amazing. All right. So then you have, as a system, you do have the conservation of mass, momentum, and energy if you properly weigh with your masses. So you have to trace that. And you do have an entropy, which is something, by the way, we don't use the entropy for the existence theory, neither the LPS, but we use it for the theory. Okay, I will not have time to get into that, but let's see. So the Lebesgue bracket, that took us a lot of time because the Lebesgue bracket, we try many things, but it has to be the one that enable us to do the energy identity, that enable us to do the angular averaging and define a contractive constant. If you don't do that, you're doing. All right. So the contractive constant control the dissipation of the gain term, and the fact that you have the energy identity gives you a very good control and doesn't deteriorate the superlinear form of the moment system. And so we actually look at the LPK spaces just to give you the framework is that you're going to have with this LP weighted norm, and it's a vector value. And we know from finite spaces that you can push most the convergence properties. Everything that you need is going together. So then the question is, can you get the lower limit? That we did with Milana in the first paper we did together in 2018, and it's very unfortunate that when we came out here, we actually in the published version we did a. It was bizarre, but we put it here that was the maximum of the piece, and it was the minimum. It's really like a typo. But it is all corrected. And if you are interested in really details, you go to the archive version 3. But we did it for 3 dimensions, and there was some other thing. And so with Erika and Milana, we revisited the extension to higher dimensions, corrected this estimate, and actually added a few more things. And that is almost finished. So, okay, so the invariant set for the OD theorem in Banach space. I have a good Banach spec. I have to show you that I have an estimate, but the moment estimate will come up in a minute. So what would be the variant set? The invariant set is essentially the same thing we form here. Sorry, we form here, which we formed before, which is to take functions that preserve that they have zero momentum, they have the mass and the energy bounded in between two constants that are independent of I, and that you have a little bit of 2 plus epsilon moments, and when you say M is the Lebesgue moment, and that gets to be bounded by these quantities. But in fact, actually, this you can put any general constant. Then you have an existence and uniqueness theorem that says that indeed it's in the same space because present. So the question is, how do we get the 3 properties from present? So we start first with moment estimates, and for moment estimates we need the energy identity. The energy identity again was a lot of work. Couldn't find it. Milana came one day and says, okay, another problem. She was coming and said, humble. But I said, congrats, caller, to ask him. And I said, oh, he's thinking another week. And then she went home and tried with MATLAB. if he could do it. And he tried with different entries, and it was always smaller than one. It something that we couldn't get this quantity. And then with the confidence that was here, we within 10 days. So it's a very interesting. So I'm a madman that numerical, the numerics are extraordinary to aid our understanding. So it's really good. And so finally we found it, the split. The split is you have to put a convex combination that adds up to the energy. That basically means these are not going to be just 1/2, 1/2, right? It has to be something else, 1/2 of the energy plus 1/2 of the energy. So it's, or sorry, the P plus Q and P plus Q have to be, you can put a splitting on the energy. The second one, right, and it's all written, this is in the first paper of Milan, the one that is published. So here, what we did is we take now it's at the binary level, right? You take the bracket for VI prime and the bracket for VI prime for VJ prime. And then try to see if it has this split, and this is the split we were looking for. And that it has to be something that it really is less or equals than 1. And the split, what it does is generate a form of center of mass and relative velocity, but with the energy. That's exactly, I mean, you go back to how you form these identities, and that's exactly how. And it's important that you have all equalities. There's no inequality. And so then the split of so the quantities that are here, which is SE and SE, blah, blah, that SE is exactly captured by this form. Even we have to reassess what was the bracket in order to get these things. So it was really like a piece of puzzle that we have to do everything at the same time. If we couldn't succeed on this, we couldn't move forward. And so once you have that, we actually started to look at numbers where we're high enough for which I get what I like to call the angular averaging lemma, which is still here, you call it the angular averaging lemma. And it turned out that it works and appears a contracted constant. And that contracted constant is this part you get to see here, right? Which you can split this K to the 2. The leftover of putting what is in here, which would be this decomposition, can be integrated and is smaller than 1. And that actually in the integral is the constant CH. I don't show it here, but it decays, and you get that all of them are bounded by its own L1 of Bij. The norms can be all different. Bij is the same as Bji, but it could be different now. And you cannot renormalize like you do for the scalar case, because it would be really very complex to manipulate. You would have always something like the other. The important thing is that you need to start by a particular K star here. It's not just that you start above 1 or 2, as we call it in the elastic case. And the reason is that, well, you see the diagram later on. And so the way, well, okay, here's a description how we got them into pieces, but somehow we can say, for instance, if B would be in L infinite, then we can get the rate, and the rate coincides with the rate that you get for being an infinite for the scalar case, and that allows you to really calibrate very well what is the contracted constant, and so the contracted constant combined with what you get from the loss operator allow us to identify the global stability condition, as I call it, or coerciveness, which is something that you should be multiplying the negative term. And the reason of that is that, the reason is that you are actually looking, and when you look at this, is the maximum of the mass ratios, and this is the minimum of the mass ratios, a constant that depends on those things, and you can see how you trace this constant specifically. And what it really matters is you don't start by any k bigger than 1. There is a k bar, and the k bar is actually classified here, and the k stars were here are the ones that you have this condition for each k. Okay? And for this case, the condition is the same for ijj. Okay. So, all right. So then you get to see, I always like to show this picture because this basically said, all right, well, how that translates into stability, right? So what do you need for the two of them to be stable? Or how many moments? So what we put up here is what happens if you take the mass ratios 1/1/2, which is the elastic case. If you take the elastic case, it's the black curve. It's always stable. You see, start low here for k bigger than 1, and it goes back and it goes very fast. But if you actually open to the purple, put 1/2 plus 120 on one side, 1/2 minus 120 on the other side, just a little deviation. You still are fine. But you go to the blue and something happens at the moment number 10, right? It's a little instability. You're just moving 10%, right? Out of 1/2. So it's really, you know, and even here is plus 1/5 minus 1/5, and by then it's really very unstable unless you start to put. So you see here is the crossing for which you get stability. So the bigger difference between the mass ratio, the more it takes more moments to get to stabilize. So the K star would be basically in choosing here. So if you deviate from 1/2 from 1/5 up and down, that basically means you're going to need at least whatever 36 moments. Electron and ions and disparate masses is I did the calculation here. It would really a very, very low bar. It would need 5,000. But you know, when people is trying to do calculations of electrons and ions in the same scale, the mass ratio, by the way, these are comments, right? Because I'm not claiming that you can actually, it's going to have the same estimate. But you do, what is clear is that what they do is that they assume that the electrons are always going to be a Gaussian. Because you really need infinite amounts. And if you put a little bit of a tail, then it's going to get out. So even to cut off the domain when we do calculations, that is an issue to take into consideration. Because you can start with the data and you have to see how these things are being pushed out, because it could become very unstable. So that is, and this is for hard potential. Then the moment, so these, and there are these two dilemmas, but now you start to see the thing. Here is the propagation and generation estimate, but we get that the collision operator has a bound, and then you can do the moments estimate until you control the bound, which is what forms the polynomial, ordinary differential inequality for which you can get estimates. And you get the superlinear term, you get the AK is the coerciveness, and it's the minimum now of the difference that you had renormalized by the masses. So somehow, you know, you start to collect all of that. These are positive quantities, but you can make it work. For a 2x2, it would be easy to trace it out. And the upper bound, B, which is the estimate we get here, here. So here you see the moment, the Lebesgue moment in a vector value space, which is super linear, The gamma bar is the collection of the minimum of all gammas renormalized by the k-1, so it's not the gamma over 2 in this case. And then here, the bk, we actually estimated by a form pretty much like I show you later. This is part of Erica's thesis, and actually we incorporated soon after we have all the estimates for the scalar case. And it turns out that you get then this nonlinear ODE, and then we get that this is going to be controlled by the maximum between the equilibrium and the initial data. And then you get the propagation results exactly with equilibrium here, and the generation result exactly as we had. So what I'm trying to say, once you get to the point that you can write the moments, the rest is done. Okay? And then, okay, so here are the forms of the estimates again, moments, generation, that is not needed to get to see exactly the two results. The present goes along, because all you need is the moments estimate, right? And for the collision moment is to get the existence and then the extension to the other, to the lower cases. Still, you always, because of the stability, have to be about K bar, which is the maximum K star. So if you go very disparate masses, then you need much more. And you have to go to the stability of the largest, so the lowest one is that have, or the lower mass, which is the one, the lower mass ratio, is the one that takes longer to study. And so you do have the same qualitatively result, exactly the same space, right? Where now these are, we call it L12 and so on, but these are the Banach space with the vector value. And then the exponential moments come up, because the proof of exponential moments, I'll be frank with you guys, it depends on the moment equation. That's independent of the entries for variation. All we are doing is taking the moments, taking the estimates of moments, and showing that they are summable. And in fact, that basically is the proof is to look at partial sums and look at whether that converges. That is something we develop. What we left did work with a part of elastic condition, geometric series, but then we started with estimates using partial sums with, say, Trevor and Boltzmann and Ricardo. And so now what we do is extend that machinery. We actually did it, found the neutron inequality. So the proofs are better in a sense. We repair one mistake we had in the paper with Jose Alfredo and Boltzmann and Ricardo, but also we are able to classify now the rates. And now this is what I show you in the previous slide for the scalar case, this rational function of the coercive constant, and now I can tell you exactly what is the rational function of the coercive constant. And this C is gamma over K-1. So you really trace it to the bottom. It's not simple, right? But it's there. But it's computer, right? And then Kahneman representation goes along, and I'm showing you just for one species, because you have to check it that what happens with the QJI, all right? And those things are actually, these representations start to change a little bit, because you have to change the GI and the IJs with the JI, and there is also a relationship that one should know. RIJ is conjugate to RJI. So 1 minus RIJ is RJI, but they appear in different places. And so when you want to do the calculations, you have a slightly different terms in the integral, but you can collect the constants, okay? And there are up to 4 different constants, which are the 4 coordinates that appear inside. And then And then you can, okay, associate norm, and you do this and calculate the Kahneman representation once more to pick up maybe an extra thing to do the gain of integrability. And the gain of integrability is based on the calculations that we did. But again, it's extended to the norms of Banach spaces, except that we were very careful and did check all the calculations. Okay. And then you start to have Young type inequality first, and then you can actually do it without weights. And then we start to put the weights, and with the weights, we use again the ideas of Young, the gain of integrability, the calculation of the L2 case for doing with the Kahneman integral representation acting with delta, and we started to do there is a lot of epsilon Young interpolation that or inequalities that come out very nice, and essentially get all these functional analysis of LP that enables you. This is really, these are that were brought in by Jons and more then we use them with Ricardo to get exact form. So the difference that we have is that they usually said, well, there exists a constant that is positive. It's that one that you can subtract. What we said is we found that constant. That is in the paper 2011, but now we actually are a little bit further, which is the estimates that corresponds. And let's see if I find them here. I'm trying to first, this is to get the exponential, the L infinite ones. Then you get the calculations of the infinite ones using the strong form of the conditional form. And then we can do really an improvement on how was the calculation of the LP estimate and the classification of the constants. So basically, we can tell what these constants are. I'm not saying that they are sharp, but they are not just the existing constant. I say at every step, what is that constant? Okay, and I think they are very important for numerical representation. And the interesting thing is that here we do this splitting of B in that it's been shown earlier with Alonso. And by that splitting, what you do is you buy a good estimate on LP for L1, B in L1. That's okay. So that is something that came out of all. We did it for the scalar and we did it for the system. Let me see. Oh, it's over? Yes. Oh, okay. Well, okay, sorry. I have no time to talk about polyatomic. And well, yes, maybe I was going to say something. Okay, for people that is interested, I'll be happy. But here is a few components. It was not much going to be said. The lower bound is there, the moments estimates are there, the compact, we call it the compact manifold, which now we have partition function, and so on. So the collapsing to that with the LP theory is slightly different because we have the polyatomic but we figure it out. We are using the technique that the engineers call frozen part. And it's that is what the polyatomic mass collapses. Because they assume the energy constant. So there's not. So what is left to do is Sobolev regularity. We did something with Alonso and Taskovich a few years ago that we have finished one, some details with the new work for the scalar case. I'm working with one of my students on the Sobolev regularity and decay rate to the statistical equilibrium for the mixtures. And, for polyatomic, we are doing now this Ricardo and Milana to put the mixtures and polyatomic in the same model. So you can do that. And I hope I have some good students, someone else, to do some of the simulations. I would love either spectrum method installation or things that we do have. Those are collisions in the other.
System that have very disparate methods, for example, electrons. Does it make sense to look at the moment at different times? Yeah.
Yes, I think you have to. You have to. In a sense, so you have a system of moment equations, right? I mean, instead of having just, I mean, I take the moment inequality, but for the mixture, I would have as many moments equation as a species. So you start, and then you can label them. That's what I'm working with my student, right? I mean, it's the highest, the next one, and so you would you saw what is the stability time for the one that, I mean, one of them is going to dominate, which is the one that has the highest mass or mass ratio, is the quantity that is going to stabilize, right? But that doesn't mean that the system stabilizes. And then what the engineers do, I have a colleague, they have a fantastic heuristics and works. Irene M, he teaches the answer along the path. And they have done heuristics that say, well, you know, they said they estimate more or less what is the scaling, and it's they just do physics, right? Which is the more as well, the mass ratio should stabilize in this time scale. And so what you do, you assume that that species is stabilized, it got into a Gaussian state, it will get into a Gaussian state. And then you remove that equation and replace it in the next equation by that. So you have a linear term now with a background and the other one that is species, and then you have to do it iteratively. That's what I believe. I mean, that's what they do. So in a sense, where people say they replace the mixture by VGK closures, you have then assumed that you have waited an enormous amount of time that may be very far away from your initial data. If your distribution, you cannot tell for a mixture that it seems to me that the probability distribution is Gaussian at any time. Right? And I'm not sure even what it means. I mean, I had a video on the dynamics of mixing, and it was heavy particles and light particles, and you can see that the heavy particles stabilize, but the other ones take longer to stabilize. And the video is done where you have heavy particles on one side and completely separate. And you know, I'm not a physicist, I've never seen these experiments myself, but I watch video, which are simulations. So in a sense, I don't know to what extent you can actually come up with a good time scale to BGK, except that you put a lot of moments. If you put a lot of, you start with all of them with Gaussian tails or almost Gaussian tail, then you are going to do fine. But still you need space. I don't know. Yeah.
So the one species stabilizes quicker than the other one, and then you can regard that as a background when you get to linear.
Yes, that's what people do.
And that's the dominant contribution. The linear part or the other one?
That's interesting. I'm trying to see We did this work with Bobby Beth. Maybe if I think a little bit more, I can give you a more intelligent answer. But the first thing that comes to my mind, we did that, for example, for macromolecule and looking at self-similar solutions. And we said, well, you have a linear contribution that is going to cool down very fast. The non-linear part develops self-similarity, the power field distribution. So that basically is telling me something that the one that survived may be actually spoiling the dynamics if it goes to something that is heavy. And once you get in self-similarity, well, that you have a range of stability for binary interaction, and it could go completely to a direct delta, or going to the distribution in one, or it could go to a direct delta, or it could end up spreading them out. Because it's not a very robust stability that will start with well initial data that you control the presentation. So the answer to that question, I don't know it yet, but people are very much sharing about that. So
there's a related question, because if I didn't catch it completely in the slides, but if you assume a lower bound for the densities of all the species, which suggests that maybe your estimates get worse and worse if you remove one of the species. Because you have always this bound below some constant small.
Oh no, that is okay. So that is among all the possible species. So if you would remove a species, you still have it, right? And you have it at the yes, but they still have it, and I believe it will have to count.
Okay.
No, I think it's okay.
Continue.
No.
Come.